Hello, everyone. Welcome to our physics colloquium. This is the last colloquium of this year. As always, we should thank the physics department and INFN for supporting this event. As usual, after the colloquium, we'll have like question and answer, and there will be some refreshments served outside. I'm told with a Christmassy version theme. Okay. So it's our pleasure today to have Tilman Plehn from the University of Heidelberg. So Tilman is a world-leading expert in particle physics phenomenology. During his very long career, he's worked on many different aspects. When he was young, he used to do high precision calculations for things that do not exist, like supersymmetry and all these things. He also worked a lot in the pheno side, so tried to deliver computer programs that one can use to do phenomenology. He was involved in what's called Prospino, MadGraph, and similars. Then he sort of switched interest, and he got interested into jet physics, and he developed one of the tools that for a long time were used by LHC collaboration to identify jets coming from tops. And in more recent years, he's grew into machine learning techniques, and now he's a very enthusiastic supporter of this revolution, and I'm sure will give us a very interesting talk too.
Oh, it's fine. So, yeah, thank you for having me. It's a great pleasure to be here. Thank you for the kind introduction. Yes, I worked a lot of my time on things that don't exist. But I didn't know that at the time, experimentalists only told us later that it doesn't exist. And what I'll talk about today is machine learning as applied to particle physics, actually, to LHC physics. And that's something I started almost 10 years ago. So, and I call this my little midlife crisis project. So basically, other people buy themselves a Porsche convertible, and I decided I'd rather do machine learning because it's more fun. However, I think what's really important for me to emphasize every time I talk about it, I'm still a particle theorist. So what drives me is the classic questions of particle theory, which is dark matter, matter-antimatter asymmetry, the origin of the Higgs boson or the Higgs field. These really fundamental physics questions. And so what I'm going to try to tell you about is how machine learning helps us answer these questions. So we have a bunch of questions. This is, by the way, Peter Higgs in front of my blackboard in Edinburgh at my office. And then after he'd drawn the Higgs potential on my blackboard, I never used the blackboard again in my office. So why LHC physics and machine learning? And if you think about it, there's a couple of defining aspects of LHC physics that lead us that way. And first of all, we're asking fundamental questions. That's actually nothing that leads us towards machine learning. That's something that drives smart students into our field. But then what we do is to answer these questions, we use a huge data set on the experimental side, and we use first principle precision simulations on the theory side. And what's important when we talk about machine learning is that, when we compare those two, we have a little bit of a fetish with, precision and uncertainties. More than most other fields, not all, but more than most other fields, and that is also the theme of how we use machine learning. And we have a very successful past, we measure total rates, and we did analysis inspired by simulations like I used to do, right? You tell the experimentalist, this is how you would find supersymmetry, and then they look and they don't find it. And we actually, the Higgs discovery was driven by theorists, right? Telling experimentalists where to look, and then they found the Higgs. Unfortunately, this was also the last theory prediction that came true, and that was 64. Since then, we've been struggling on the theory side, which drives me to, or drove me to thinking more about how can we more systematically understand the data in terms of quantum field theory, though, still me remaining a proper theorist. So what do we do then? We start with our precision simulations. First principles means we write down a Lagrangian, and it's all quantum field theory. Start calculate scatterings. We simulate the collisions with our standard event generators, and the experimentalists simulate the detectors, and then we in the virtual world defined by our Lagrangian, we generate a set of LHC events that are really like how LHC events looked if that Lagrangian was true. And you can put into this Lagrangian anything you want, any new particle or old particle, or leave particles out, what you want. So in the language of my machine learning colleagues, what we do is we produce digital twins of LHC events, right? And we produce fake LHC events in a virtual world, and then we compare. We simulate them in some virtual world, we compare with the real observed events, and that tells us which world is true. And then, of course, I hope that we'll still find new particles, right? That could be like beyond standard model physics. If we're unlucky, in the worst case, we will just understand the standard model extremely well, right? And really understand the entire LHC data set as part of the standard model. And one thing that's important to me, and that is driven by machine learning, one thing I want to do is I want to publish results that can be used by non-members of the collaboration. So how do I actually get a broader audience, to use LHC results? Because I think it's a hugely attractive data set. This, by the way, here, this is our simulation chain as written by a theorist. So it starts from the theory, and then it has all the things that we do as theorists, like the scattering, the decays, QCD effects, ask him, ask Simone about it, part-time shower, fragmentation. This is kind of more or less theoretical. This is okay. And then this is what the experimentalists do. When experimentalists make the same figure, this is all theory, and then they have their different stages, of course, right? So it's biased. But that's, that's about describing my life after all. For those of you, I don't know if everybody knows about LHC data and the structure that we're dealing with, let me just really explain roughly what we're dealing with here, because I think people aren't always aware of this. So Atlas and its CMS are general purpose detectors, which in practice means they're big. And then we have more specialized detectors, which are smaller. They cover less phase space or certain dedicated phase spaces like LHCb, ALICE, or Phaser. And then we have thousands of scientists per experiment. Atlas, I think, has 5,000 authors. And then they built enormous detectors. So you have the PP collisions somewhere in here, and then you have detector the size of a house. That's a person, right? What's important for those detectors in terms of machine learning is they produce a lot of data just because they're very big. I mean, the detectors have very big, many components, and they produce a lot of data. And what makes things worse is these collisions happen at a rate of 40 megahertz. So the rate of the LHC, if you want to get an idea, the time between two collisions at the LHC that produce hard events is the same time that it takes a particle with the speed of light to get to the end of the detector. So the moment the particles have reached the end of the detector, the next collision hits. So we're producing very, very large data rates that way. To be precise, an Atlas event has roughly a megabyte size when you do it, and the data stream of Atlas is petabytes a second. I mean, that is some data rate that even Google people like, right? And we don't have to be ashamed of this. And if you want to understand all of that, that's quite a feat. And what we measure is in the detector is actually quite simple. What we measure is stuff like energy of a particle, the momentum of the particle, charge of a particle, maybe the decay length, right? I mean, these are things that you all know. This is not very complicated. It's not a very complicated n-tuple of things that get measured, really, when we reconstruct these particles. As a matter of fact, for electrons and muons, it's very easy. You just it's a muon on a muon, not a muon, and then you measure the momentum and the energy. For jets, it's harder because they split and they fragment. So a jet that comes from a quark or a gluon is typically described by 50 particles, so 50 energy momentum measurements. Which basically means every time you have an LHC collision, the data you produce is an n-tuple is just a vector, right? I mean, 100 or 200 or 300 of them, right? So this is our data format. What I'm saying is it's not very fancy. It's basically a bunch of energy and momentum measurements. However, it comes at real big rates, right? So what we have is we have data that we understand in principle pretty well, and lots of it that we need to sift through. And the goal is to answer fundamental questions like, for instance, where does the Higgs boson come from? So, in a nutshell. Machine learning applications here, I know in general people are doing a lot of that. So if you make a list of machine learning applications, Well, it's data selection, it's data compression, object reconstruction, object classification, the actual analysis, simulation, theoretical calculations, event generation based on that, inference, simulation-based inference, or in other words, everything. Everything we do at the LHC, I think, will at some point benefit just because of the amount of data and the speed that's required for machine learning techniques. Right? The level of sophistication in machine learning is very different for these different tasks, but I think we like everything we do right now where people are turning around and checking if we can improve it. I promised to briefly talk about, because I mean, you can nowadays you can't talk about like physics and machine learning and not like enter this like in a minefield of the Physics Nobel Prize. Because I have never, I should say, I'm quite old, right? I have never seen a Physics Nobel Prize as contested as this year's, right? I mean, people have gotten Physics Nobel Prizes for all kinds of stuff, but I have never seen, like, even in the social media, so much, pushback for that. And so what I did this week, I actually went and looked at the Nobel lectures. I can recommend them. They're on YouTube. You can look at the Nobel lectures, and they're really cool. And so I watched John Hopfield. And it's kind of funny. So the way he describes himself, I mean, he is actually a physicist by training. And then he did a lot of things. But what he will argue is that he's a physicist in search of problems. And at some point, the problems that he was thinking about became more like biological, or chemical and biological with time. But he will insist that, physics is a point of view, is I think what he says. It's actually on his slide. So that guy is a physicist. And he would argue, if you're a physicist and you solve problems using your physics toolbox, you're a physicist no matter what the problems are. I totally share that point of view. Geoffrey Hinton is totally different. He's not a physicist by training, but I watched his lecture and I said, boy, he knows more about statistical physics than I do. He would totally pass as a physicist. And that includes the question session he would pass as a physicist. So he basically, when he talks about minimal energy trainings, and about thermodynamic problems, about likelihood maximization, and then he explains the properties of thermal equilibrium and so on and so forth. I mean, this is serious physics. So when you read their work and you look at, you hear them, you notice that this is maybe not only one of them is a physicist, but the thinking behind these, behind these ideas are serious, very physics. Another argument I want to make, has anybody ever bothered looking at Jeff Hinton's Google Scholar thing? So this guy collects 100,000 citations a year. So good physicists, I don't know what we do, 2,000, 1,000, 3,000. So if you have 100,000 citations a year, I'm sure there's more physics citations in that than to any physicist, right? I mean, so yeah. I mean, so think of Hinton as the superstar of global science, if you ask me. They call him godfather of AI. By the way, he graduated from Edinburgh in AI at a time when I didn't even know AI existed there. Okay, so for me, neural networks are much simpler thing. For me, neural networks are basically functions, learned functions. So I learn a function, f of x. I describe it in terms of a bunch of parameters, just very much like a fit. It's just the only difference between a fit and a neural network is it's a lot of parameters. It's millions rather than 5 or 10 that you have in a fit. And then you can use them either as a regression function, you just learn a function, or you learn a function that then works as a probability for classification, or you learn a function that you can sample for. So it's a function of a random number, it produces some distribution, in which case you have a generative network. Or you have a function that samples under a condition of another function of input that you give it, which is conditional generation. And this is currently the state of the art in machine learning that drives most physics applications. But in essence, it's just a learned function. It's nothing more than a very, very high dimensional fit. What it means in practice for my physics thinking is it taught me one thing, and that is complexity is a feature or an opportunity, not a problem. Because when you can work with very, very high number of dimensions and you can use data to understand more data, you're much less scared of complexity and amounts of data. It's a good thing. Having lots of complex data is a good thing that allows us to understand stuff. Historically, people always argue that colliders shouldn't run at too high luminosity because we'd be confused by too much data. That was the problem of Hera, for instance, right? So, so this has changed. I'm a theorist, so there can't be a colloquium with a bunch of formulas. And so let me, one thing I wanted to, tell you about a little bit about this, so how do I train a network? What does machine learning mean, when you look at this kind of more mathematically or more theoretically? So imagine you have, something, you measure an energy as a function of phase space, right, of your produced particle. And now these particles, like a particle doesn't have a well-defined energy, but it has a probability distribution over the, of the energy. And then what you measure is the expectation value of this. This is just statistics. There's nothing machine learning about this, right? What machine learning does, it rewrites this expectation value here as the E here stays as an internal representation, and this is just a completeness relation. So probability that the energy is described by a certain configuration of parameters, and then times the probability of the parameters given the training data, right? I mean, this is really an internal representation of your training data that you want to understand, and that is the neural network, because what you do is, you don't want to evaluate a probability that something you have a representation giving the training data. You want this representation to be universal. You want to know it once forever, right? You want to generalize beyond your training data. And that is called network training. So in this expectation value here, you replace this probability evaluated on the training data by a universal function Q of theta. That's your network. And when you think about that, well, then how do I train a network? And that is the genius aspect of it. You train the network of making two functions here similar by minimization. And minimization is something we physicists can do extremely well. Actually, there's hardly anything we can do as well as minimization, right? Minimizing we can really do, right? The entire statistical physics field is minimization when you think about it at the end of the day, right? Lattice gauge theory is minimization. Measuring stuff is often minimization. And the only thing you need to know is that, minimizing something, two functions, you have this so-called KL divergence. Divergence is one measure of the difference of two functions, which is a log ratio here sampled over one of the two functions. And it's not unique. And you can pick, this is the most convenient way of writing it. Now, the only problem is here, this P of theta given E train. I don't know what the probability of theta is given E train. However, if I have data, I can generate it, I can sample it, I know the likelihood the other way around. So I can actually sample the probability of my training data being reproduced given my parameters in my network. And that's the only non-trivial step. You put in Bayes' theorem, and then you write this function here. And that's what we minimize. And the thing that we minimize is called a loss function. And so what we write down here is, this is the loss of a neural network. It has two terms. This one here is a likelihood term, sampled over this contribution here, and this one here is a KL divergence. And the reason why you have never seen that function as a loss is because it's very complicated. It's called a Bayesian network, but you can simplify it. For instance, if you say, actually, I only care about the central value, I can replace that Q of theta with a delta distribution for theta equals theta 0. Just you learn not a distribution of thetas, you learn a value. In which case, this likelihood here, simplifies. Then you say likelihoods are Gaussian. They're always Gaussian. Then the log likelihood is nothing but mean squared error. And this is the loss you all know. What's cute here is when you derive it like this, and this is something that you probably won't know, is when you actually look at the KL divergence between two Gaussians, you get this kind of term out, which is an L2 regularization. So I can derive, on one page, I can derive mathematically, right? Formally, I can derive what I have to minimize to train a network to learn something. And I like that as a theorist because it gives me a sense of science, right? Hard science. And you go from here to here. So loss functions, it's nothing magic about them. Loss functions are really just likelihoods or probabilities that your network parameters describe the data. And then you simplify them if you can, right? But that's the definition of a loss. Let me briefly run you through a bunch of applications that we have seen in particle physics with machine learning just to convince you that really it transforms our field. The first one is top tagging. I used to work on top tagging with him. We used to go to the same conferences until I was not allowed to go there anymore because I did machine learning. But in any case, so the question is, how do you tag like, a jet, which means how do you identify the partonic content of a jet? How can you tell a jet that comes from a quark, from a jet that comes from a gluon, from a bottom quark, from a charm quark, from a tau lepton, from a top quark, from a Higgs boson? All of these things can give you jets, and how do you tell them apart? And this is a machine learning task. And I want to show you, this is from a recent thing we did. So this is the time of publication. This is where machine learning hit. So this is the background suppression at 30% signal probability efficiency for a top tag. And here you see why we are transforming our field, because my old top tag that I wrote was around 200, I think, I forget, like something there. The first networks were around the same time. And now we are able to suppress the backgrounds by a factor of 15 more. So our background suppression with a neural network is a factor 15 better than it is with the best taggers that we used to be able to write in 2000, right before this hit. In other words, if you want to identify, do anything with jets, you have to use machine learning for these kind of taggers just because they're so much better. There's no question if. The question is how, but if is not a question. And this is a field that has this is basically the most advanced part of machine learning. Particle physics started 2016. By the way, that has a name, 2016. That's for young people. That field was started by a graduate student with the name Ben Nachman at SLAC, who basically wrote he wrote a paper machine learning, what was it, image-based jet taggers or something like image, and he revolutionized our field. That guy's young. And he did this, he revolutionized our field as a PhD student. So here's your challenge. He's also very smart and very nice. Something else, particle flow. Here's a problem that every experimentalist has. You have two kind of detector components. You have a tracker. A tracker measures stuff extremely precisely, except you only find charged particles. So half of the particles, or whatever, fraction of the particles you don't see. And then you have the colorimeter. The colorimeter measures all particles, but much worse. How do you combine those two pieces of information? Downsampling everything to colorimeter resolution is stupid because you're throwing away a lot of information from the tracker, right? So how do I combine two very, very different resolution, pieces of information? This is called, in particle physics, we call this particle flow. Here is the computer vision particle flow with contribution from Genoa. This one is CMS, same thing. You do this using machine learning. Do that using tools that people use for gaming. Because if you think about it, for gaming, you have beautiful images, and it's clear that the image in your background cannot depend on where you stand and where you shoot or whatever you move, how you move. So they know how to combine these different levels of information. Parton densities, I just have to mention this every time. Everybody, experimentalists say, oh, we will never use neural networks. You say, people, what do you think NPDF stands for? So particle physicists have been using machine learning for their parton densities since 2002, I think. Famously, the first NPDF paper was written in Fortran, machine learning in Fortran at the time. By now, this is a driver in machine learning theory because it tackles one of our core problems, and that is precision and understanding the precision of a network. So if you want to learn more about this, go to Milano. It's 2 hours on the train. There's the world experts in precision machine learning and physics sit there. Fast event generation is another one. We're working on event generators. You want to generate events fast and precise. They have lots of different modules. They're called either Sherpa or MudGraph. And Simon Badger, by the way, is working on them in Torino. And so now, one of the questions, for instance, can I learn a function, an amplitude or transition amplitude, precisely? And if yes, how precisely? And if how precisely can I keep track of the uncertainty in that? This is a problem that, a question that seems very simple. The problem is that typical machine learning in industry, they don't care about learning a function to 5 digits. It's not their problem, which is fine. I'm not complaining, but we need to do this. So this is a research thing that we are working on right now. How do I learn a function to 5 digits? Sounds trivial to somebody who just does theory calculations on the computer because you always get machine precision. But the neural networks typically give you 1% in their estimation. In theory, again, like, you have a very active group here, do theoretical physics. Like, for instance, one of the big questions is the experimentalists, like, they give you results and they like report likelihoods, right? I mean, and in principle, everybody can use them, well, if they can use them, right? And so the question is, how do I make these likelihoods usable, public, fast, efficient, all of that. So, this is like, a nice little study. So, I like that figure here because it's like, it shows you there's a lot of 100 dimensions, physics and nuisance parameters in these likelihoods. And that is proper theory, right? I mean, what you do here is proper theory. And then one of other my theory highlight papers is string theory. So like, you know that like string compactifications, they don't always lead to like inhabitable universes, right? I mean, you have certain boundary conditions, now find them. So what these people do is they play AlphaGo in the string landscape. And they find new stuff. I mean, you talk to them and they do find new islands of habitability in their string landscape. And they construct like Calabi-Yau compactifications explicitly for the first time. Which means I'm just showing you these 6 results to show you that from experiment to phenomenology to theory, there is like, there's applications all over the place. Just look for them, you'll find them, right? You have like, some problem, try machine learning on it, chances are it helps. Well, maybe not. We are lucky. It helps, and if not, try again. Right. Let me just like, mention like, one example that I'm particularly proud of. It came out this week. And this is something, I'm also fighting with the experimentalists mostly because they tend to be conservative. But I mean, if you run a big operation like a 5,000 people experiment, you better be conservative, right? I'm not blaming them, but they are very conservative. So they have the colorimeter, and they want to calibrate this. Calibrating colorimeter means for every colorimeter output, which is some kind of phase space, you want to know what's the ratio of the energy, like, that you measure to the energy of the particle that the particle really had, right? This is a calibration function. It's an order 1 function, if your colorimeter is any good. So I said, we should do this, we should learn this, and you know what? We should extract that with an error bar, because we can. You can actually learn functions with error bars based on data. An experimentalist, like that one experimentalist, Peter Loch, he said he postponed his retirement and said, like, I'll do that with you. And the uncertainties that we're looking at, for instance, the data is noisy. Our network is not very expressive. The data representation we're using, the 5 space parameters, is garbage, whatever. Like, you have all these kind of limitations. And now the question is, does it, like, can we make use of that information? And I'm skipping the part where I say, like, we get the best extraction of this function, because that's quite obvious that we will, because of, like, networks just do what they do. But here's something as a story. So this is the uncertainty that we found. And you would expect this uncertainty to go down like this. And it doesn't. And so like then the usual thing happens that my student made that figure. I said, OK, find the mistake. So like, he came back 3 days later, didn't find a mistake. It has to be true. I said, like, no, can't be true because uncertainties don't go up like this. And so like just can't be true. So like we went through this for like the usual 4 weeks. I know you know this interaction with your supervisors, right? I mean, they insist and you insist. And then after 4 weeks, maybe the supervisor agrees that the student is producing something that makes sense. And then we plotted these weirdo high uncertainty topoclusters, they're called, colorimeter outputs in the actual space. This is the radius of the colorimeter, and this is like the z direction, the beam direction. And look, I mean, they sit all there. And that is what we would describe as, the shit part of the Atlas detector. This is like the part where it's not a very good colorimeter. And if you ask the experts, they will actually admit it is. And it's nice the simulations know that. But now we have a calibration function that knows about the parts of the detector which are good and the parts of the detector which are not good, which is something that Atlas didn't actually include in their calibration until now. So here is something that I can help with machine learning. I can help my experimentalists to be in being more precise. And that's kind of a nice message to send them. And this is, by the way, a very simple network, really, when you think about it. Now, what I want to talk about, though, is not just like, the simple applications. You all know from the media that like what drives machine learning, the revolution right now is generative AI. It's like ChatGPT or like similar tools for images or similar tools for anything. Famously also for like, LHC events. Yeah, so what you do there is you learn some kind of a phase-space distribution here, and like, you can simulate event generators, so then it's actually like, the distribution of top quarks where they fly, or it's calorimeters, in which case it's the way that, a pion hits a calorimeter and makes a little shower of hadrons or lepton, or photon shower, right? It's all like, and you, then you employ generative models and generative networks. And generative networks have in the last 10 years or 15 years have like, evolved immensely. So everybody started with variational autoencoders. That was before I did physics and machine learning, so I never used variational autoencoders because they're not very good for that purpose. They're not very precise. So we joined the race using GANs, generative adversarial networks, but it turns out they're also not precise enough for us. The reason is that they are like the game theoretically that you have two players play against each other, like in training the network, a network that the generative network and another player that checks how good it is. And it's kind of funny. I love this concept. Except when you set up such a network, you forget that two players can sometimes agree on a real garbage compromise. And this is what the GANs sometimes do. So when you want to be precise, don't trust these players, don't trust the GANs, because sometimes these players will just decide, okay, let's just call it a day, like, compromise is good enough, we go home. And this is what happens. So that cuts into your precision. And then in recent years, normalizing flows, diffusion models, you can ask my local colleague here, like Ricardo, and then more recently, transformers are really changing the way we think about generative AI, right? And we are basically now currently we are rewriting all of these codes using any combination of diffusion models, normalizing flows, and transformers. So this is like the cutting edge, technically. And it makes a very big difference because it is important, precision is important, and uncertainties are important, and for instance, normalizing flows are very, very good, easy to control. Diffusion networks are a great compromise between control and expressivity, and so on and so forth. Transformers are great because they're non-local, right? I mean, language is not local. Transformers are non-local. So for instance, if you now want to encode combinatoric effects, use a transformer. It's like language, right? But sometimes you change the word order in the language by inverting the verb and the noun, and it's the same sentence still, right? With a different emphasis, and the transformer will know this. And exchanging two particles is literally the same. Yeah, so this is currently what drives our actual in practice application. Now, we weren't physicists if we don't ask exactly the same question again. So, okay, now I have a generative network. I know we share that, that hobby is so how good is it, right? It's an important question. How good is my generative network? Has it learned the underlying density? And if yes, how well, right? So we all have, our way of thinking. My favorite way of thinking is, take another machine learning tool, a classifier, give it 100,000 events training data, generate 100,000 events, right? And try and ask a classifier, can you learn the difference between the two of them? If the classifier can't do this, well, then your events are damn good. If it's not, well, then work on your generator, right? So machine learning people, by the way, say this is impossible. Physicists do it all the time. And beyond that, I mean, this is a little bit of math. There is this called, I don't know, there's a Neiman-Pearson lemma that you might or might not know that says the optimal or the best possible classifier is the likelihood ratio. And if you turn this argument around, you can say, if I have an optimal classifier, I can construct the ratio of two densities, the likelihood ratio, out of that classifier. So I do Neiman-Pearson lemma the other way around, right? What that allows me is to make this kind of figures. So I have correction factors that describe my data distribution over phase space and my model distribution over phase space. And I now histogram these things, and it looks like this. Ideally, there's a peak at 1, and there's a certain width to it. And wider networks are not as good because they have larger differences. I mean, anything that doesn't peak at 1 is bad to begin with. But if you peak at 1, the width tells you how good you are, right? As a matter of fact, if you have funny tails in this distribution, it also tells you about, if you have any, the failure modes in your network. So what we do in physics is, it's very typical. Yes, we use generative AI, but we use generative AI in a very different way that, like, you, for instance, whatever, like, Google or, like, Amazon uses it. Right? We don't generate suggestions. We generate stuff that we rely on being very, very precise. And the way we do that, we can test that is more machine learning. So that is a nice part of it. Like, it's like, you want to test machine learning tools. Actually, Ricardo has his own statistical methods, but it's like, I would say, like, use another machine learning tool and, like, check it, right? So this becomes, like, its own little field. And here, for instance, I can tell you, this is from a paper that we wrote, where we were subtly suggesting that the blue network is way better than the red. So we plot that figure in. Yes?
I can see that the blue is better than the green.
Yes.
But how can I convince myself that the blue is good?
What you can see here is, so the difference for all the events I've seen, the weight that I would have to apply for one data set to be transformed into the other is 1 plus minus a few percent. It depends on how you define the plus minus. So here I would think the width here, if you don't have any features, the width tells you is kind of the precision of the density.
Exactly. But how do I quantify whether this is good or bad?
No.
Maybe the precision I need is much more than the blue.
Yeah, so if you, for instance, go to an experimentalist and they will tell you what percentage you want, right? And then you plot this, and first you make sure there is no structure. If there's structure, you're dead, right? And then here I would argue the experimentalists tell you I need that precision, and then you say, okay, my network, well, I mean, if you're the blue network owner, you say I do it, and if the experimentalists say you need this kind of precision at like 10%, and you are the green network owner, then you're not good enough. Yeah. So I should say this is not a one-dimensional thing, right? Because it's important that you have failure modes and stuff like that. Okay, let me just very briefly talk about my personal group cutting-edge research, like, what we like most. Because, when you do machine learning and particle physics, your colleagues tend to come up. And they said, okay, but where are you really changing the way particle physics works? And that's like, we can do tagging 15 times better. And they said, yeah, but who cares, right? I'm talking about now the university vice president kind of people who say, like, yeah, factor 10 better, what is that? Like, you're still doing the same and you will not find supersymmetry, right? So the question is, can we devise at least one example where we can actually do something that you couldn't do before? Something that changes the way we do particle physics. And for my group, for my life, I have identified one of these things. Every colleague who does machine learning clearly has their answer to this. So ask around later what their thing is. Everybody has their little dream. So my dream is so-called unfolding. So here's the reason why. First of all, if I want to do optimal analysis, right, simulation-based inference, I need to simulate the signal and the background, the potential hypothetical signal and the background extremely precisely. Given the number of signals that we are looking at, there's no hope that we can do this at the LHC. Because if some model builder comes up with another version of supersymmetry that has 100 free parameters, right, you're never going to be testing this globally. So we need a better way of testing these models where we don't have to resimulate our signal all the time, right? The second thing is, when we do theoretical calculations, like we know in QCD, for instance, I mean, these are like, long-term investments. Things get improved with time. So the question is, can I somehow, like, take my analysis and reinterpret it later, given my better knowledge 5 years later? Because the student who has done the LHC analysis has long left physics, and so what do I do with it, right? So how can I update this? And the most important thing for me is, I have for a very long time also been part of the camp where people say, there is no way we can publish LHC data and give it to, like, people to work with, right? We all believe in this at some point when we say that, but it's nonsense, right? Like, we say we can't publish LHC data, and that is true if you give them the detector output of all the different detector channels, the 1.6 meg per event, and then, like, these huge numbers. But you know what? Nobody cares about the detector. What if I could publish LHC events at a level that people can use them before the detector, or even before parton shower if you're looking for a resonance that decays to stuff, right? And then my argument is, I can do this, I can give these, that information at the appropriate level to amateurs and high school students. Everybody can analyze LHC data if we work it out the best possible way. And this is, to me, the theme is forward simulation and backward simulation. So what do I mean with backward simulation? The mathematical problem that we're using here is unfolding. So I have a data here, and I have simulations at the reconstructed level, right? And this is the typical the comparison, I simulate data, I compare it to real observed data. This is where I do inference, I measure stuff. However, let's say this is before the detector, right? What I really simulate is stuff before the detector and turn it into observations after the detector. The way I turn it into that is a conditional probability. And what I always do is I start from here, and then I do that simulation and compare here. Where in practice, it would be much more efficient if I would start from here, and then look at the data and do the inverse simulation, turn it into this corresponding for before the detector, and do my inference here. Because then I can forget about detector effects. I don't have to consider them anymore. Now, mathematically, that means I have one conditional probability here that goes the one way down, and I have the inverse probability that goes up. And everybody here probably know enough math that you know that these two conditional probabilities, they're described by Bayes' theorem, right? This is that is Bayes' theorem. You turn around the two probabilities, right? Which means if I can control the prior and the evidence sufficiently, I can turn one into the other. Or in other words, if I have a simulator or neural network that does that, I can train a neural network to do that. And there's something that we are working on. Another group that is working on is the Americans, is Ben Nachman in Berkeley and Jesse Taylor and collaborators in Atlas at MIT. They do a slightly different thing. They use this Lehman-Pearson lemma to have these simulations before and after the detector, and they have the data here. And what they do is they train a classifier to reweight these things into each other. So basically, they say after detector, my two events here, distributions are given by events which have a final weight distribution, and then I take that weight distribution, apply it to that simulation, and get the unfolded data, right? So I basically avoid calculating this probability, and I basically pull and push back by saying the weights, the ratios here, the likelihood ratios here and here should correspond to each other, so I learn them here, apply them here, get that distribution. And this is what Atlas just published. This is Z plus Jets production. This is the angular separation between the lepton system, so the Z, and the leading jet. Before detector. Everybody can simulate that. You can give that to high school students, and they can give them math graph, and they'll do that for you, right? So everybody, literally everybody can understand this LHC data. No, right? So what we are doing is we're doing the same thing with generative networks. So I really want to do the pair, the data here, the simulations. I want to learn that probability from this pair data, and then I want to apply it and push it back up. So I want to learn a conditional probability. The same way forward and backward, right? And to give you an example, here's a particularly hard example, and let me just tell you why it's cute to do that. So you have a top quark decay, and you want to measure the top quark mass through an unfolded, so everybody wants to measure, you want to process the data such that everybody can measure the top quark mass in published data for the top decay products. You give people the 4 vectors of the top decay products and say this is the data, measure the top quark mass. Everybody can do this in principle. There's one mathematical complication that I just want to mention because it's kind of cute. So the problem is when you want to measure the top quark mass, your simulation has a top quark mass in here. I call this MS for simulations, the mass in the simulation. The problem is you want to measure this, which means that MS here, you don't know what that is. Data knows what MD in the data is, right? But that's what you want to extract. So you're playing around with a parameter that you have in the simulation here and that you have in the data. And that is nasty because now you learn this unfolding probability, right? You learn this from the simulation, so it depends on MS, right? It has code MS encoded into it. However, you apply it to MD, data with MD, which means your outcome here includes both. And you have no control. You have killed yourself because you don't know what you measure, right? Is this the bias from your simulations or is it the actual data? Which of these two parameters determine this unfolded distribution when I measure it? Right? You want data, simulations, you know what you put in, right? That's kind of boring to re-extract. It's actually worse than that. And this is what drove me to do this, because when you do this in practice, it turns out in this specific application of particle decays, the unfolding people know that. They told us that. That is, you have the data here and the simulation you put in, but the simulation, the bias is much stronger than the impact of the data, which means the argument here is classical unfolding people will tell you cannot measure masses of particles in unfolded data because all you get back is your prior from your simulations. It totally overwrites the actual structure in the data. And now here comes machine learning, because with machine learning, I have control over this, these kind of aspects. So what I can, for instance, do, and that's actually quite easy, right? It's like, oh, the network here learns a strong bias. Well, what in my training data if I don't give it a single top mass? What if I give it 5 and don't tell it about it? Clearly, it cannot actually learn a single mass value anymore. It'll learn a distribution, right? That distribution should cover the real mass. I can ensure that, right? The second thing is, this one here has a 2-week imprint. What if I make my network more efficient in learning that thing by just pre-processing of the data? Give it the triple jet mass and it will learn that this is a proxy for the top mass. And all of a sudden, you can do this. So all of a sudden now, you use a network. This is the generated data here, the black one. This is what the detector does with it, the blue cowpie thing, and then the resurrected unfolded data is red. And you see they sit right on top of each other. The ratio of them is 5% apart. We can measure, everybody can measure the top quark mass now. It's before detector, you can just look at it, you can plot it. Right? Like this available. For a lot more technically minded, people also want to measure the W mass that comes out. They use this for the jet calibration. And we are waiting for CMS data. Here's a story to this. I did this illegally with CMS data, and then they got on to me, and then they forbade me to publish this. So I'm showing you unpublished CMS data here because it's so cool. The thing is I can't publish it. So we are redoing the analysis now with public software, and then we can publish it. Don't worry about it, but it's CMS, they didn't like our result. I always blame them and said they didn't like it because they're conservative and we're too smart. Actually, Sophia Palacios-Schweitzer is too smart. Okay, so, which brings me to my bottom line of machine learning in particle physics. And I have 2 bottom lines. I have one for the more conservative older people and one for the younger people. So what I always tell my colleagues, senior people, I said, we are a numerical field and machine learning is just another numerical tool. Don't worry, you'll be fine. It's not going to be very different once we do machine learning. And then they're kind of comforted by this, but it's a lie. It's it's just not true. Because what it really is, it's an incredibly powerful tool that allows you to do stuff that you couldn't do before, right? It's transforming our field. We pretend it's just a smile, if we can only alienate so many people at a time. But, it's a transformative new language. All of a sudden, you learn from other fields of science. By the way, you have this entire enterprise is paid by money from data science and medical research and stuff. Particle physics, we're getting all of this for free, right? I don't have to develop transformers, right? Google spends billions doing that for me. And then here's my little argument. I like this. I took this, the 1000 Einsteins from Matt Schwartz, a friend at Harvard, who says, so what's the impact of machine learning then? And he said, well, the limiting factor in science, today's science, is we have only 1 Einstein per century. So you have only one person who really turns everything up inside out once every 100 years. And that limits our speed of progress in particle physics because we have to solve a bunch of really hard problems, right? And sometimes it takes somebody like Einstein to do this. Now, if you think of the smartness of people as a Gaussian, then he would say, take everybody, and enhance their capability with machine learning. Basically give them networks that know a lot more, that are creative, that help them with everything they do. They're still physicists. And then he said, then you shift. You shift the maximum, the mean distribution, but most importantly, the tail shifts with it. And all of a sudden you have 1,000 Einsteins, a century. And that we can work with, right? Because 1,000 Einsteins will enhance the speed of our research without doing anything to the people. It's just regular people can do much, much better science. And the way we do this is either we can improve established tools a whole lot, then we can develop new tools for established tasks, right? New ways of doing things, and if you're really lucky, a completely new idea. Something that people didn't even think about doing before. I don't know, this is up to you. I mean, you are the hopefully you have the chance to be the golden generation. The first one is a little boring. It's like what we do for a living, right? But it's a little boring. The second one is already great. Find a second one, you get a nice PhD out of this. Find a third one, and you get a faculty job, I promise. Right now, everybody is looking for these kind of things. We call them the AlphaFold moment in physics. We're still waiting for the AlphaFold moment. And I think we have to rely on young people like you to get us the AlphaFold moment. Thanks so much.
Thank you, Tilman. Questions, comments? Yep.
You made a good example of these peaks that measured very broad, and then you able to reconstruct them in a very narrow shape. Yes. This is very nice example, and probably is well reconstructed, but it works when you already know something about the underlying physics. For example, I would say one simple example. If this peak would be a double peak by some unknown yet splitting in some physical case, your unfolding would not show that, of course.
Yes. So the unfolding has two sources of information. One is the simulation and one is the data. And the structural aspects are encoded in the simulation. The detail will then be extracted from the data. So you can think of this unfolding as the structural part, the fact that there's a peak is in your simulation. The position of the peak is in the data. The width of the peak is in the data, I would argue. Asymmetries in the peak are in the data. A double peak probably is not. At some point, these unfolding techniques, because they have these dual sources of structural information, they have their limitations. That is why I say you can do with that public LHC data, you can do a lot of analyses, but you have to be very well aware to what level you unfold, so you can get your answer right. And there is still, at some point, there will be the kind of analysis that you can't do with the public data. Which, by the way, is the same, I think, in astrophysics. The astrophysics data, or astronomy data, is pre-processed, and stuff that's not considered in the pre-processing is not there, right? I mean, so in the sense, there is always a benefit to the experts doing it perfectly, and the published data kind of analysis is kind of by definition, is less deep. However, it's broader, right? So, when you do analysis, our experimental friends do them, right? They take 5 years a pop currently in analysis, roughly like this, right? Something like that for a student, which means you can only do so many analyses. And this is, I think, where the strength of published data comes in. So it's coverage. You look at stuff that, in principle, you think you have an idea how it should look, but you don't get around looking into it. So everybody turns on. And then there's a feedback loop. Somebody comes up and says something is weird, and then they call up somebody, and then then it works. But there is a different level. So if you have no time constraints and no people number constraints, of course every analysis should be done by the world expert. But we have those constraints. And so the question is, can we get around them? And I think actually astronomy is a great role model for us there. I mean, astronomy is very good at publishing their data and having other people work with it. And by the way, if you've discovered something around this astro data, and experimentalists, I mean the collaboration disagree on this, it also, they know how to push back. Sometimes not even fair, yeah.
Yep.
So I was sorry for my voice. I was a bit curious. It seems that machine learning is a bit of a black box that finds a lot of little spots where it can just superimpose and put in the pipeline. As a theoretician, do you see an opportunity to somewhat make it a bit less black boxy and a bit more informed by the physics that you know, as opposed to just using it as a data analysis tool?
Let me put it that way. I think I don't just see a way, it's my job. My job as a theorist or particle physicist, I don't even have to be a theorist, right? As a particle physicist, a domain particle physicist, my first job is to make machine learning like less black, understand what's happening. Like one thing here, what I didn't talk about, for instance, when you learn a function and the uncertainty, the network learns them both in parallel. And it turns out by trying to follow how they learn these two things, you can understand how the network learns things. So to give you one example here, this is why I'm showing it. When you look at the way that R and delta R are both learned by the same network, you will notice that normalizing flows behave very much like fits. So they define a certain, like, a typical family of functions, and then they determine the parameters in further training, right? So, like, they're quite stiff, because if their family of function is limited, they can't describe it. And that's an important piece of information when you want to work with them, right? Now, if you use the same kind of method for diffusion models, that's just a very simple theory example. For diffusion models, you notice that the family of function gets bigger. So, like, it becomes more flexible in describing things. And when then you go to transformers don't even assume a family of function. They really estimate densities patch-wise, right? And you can learn these aspects from, like, looking at the way the network trains. Now, this is an outside network kind of thing. So I would argue you can, of course, go beyond that, and now you can look into the network weights, the latent representation. And if you're really good at statistical physics, I think you can learn a lot. For instance, like, you can look at phase transformations, like, you can see how the network learns. You can look at scaling laws, how network learn, like, with epochs, like, how expressive is the network with the scaling law. There's a bunch of ways, like, things that people have observed in network trainings as a function of epochs, which are totally weird, which I would frame as a statistical physics problem. So yes, so at all levels, so this is the simple level, and then you can go from there. We should, it's our job. Absolutely. And if we don't do it, by the way, nobody does it, because, I mean, these are complex systems. I mean, I don't think we can expect the biologists, because networks resemble like a brain, I don't think we can expect our biology friends to do that for us. I mean, these things are, and this is, by the way, true for, you see from the Nobel Prize, these things are described like, these are statistical systems. Yeah, you need thermodynamics or, like, statistical physics to describe them. Yeah.
Thank you for your talk. So I have a question, which is what do you think? You think it's interesting, and what's your opinion about using machine learning for unsupervised searches or agnostic analysis?
The picture I send is, unsupervised learning is one of my favorite topics. I just didn't want to, talk about it. So the question is the following: unsupervised learning, like a very simple question, is imagine you look at top taking. Look, you want to know, what is a top jet and what is a QCD jet. I can either train on top jets, and on QCD jets train the network to, like, model the probability that it's one or the other, right? The supervised classification. The question is, can I train a network to understand that this a jet is a QCD jet, but just by looking at QCD jets. And then when I give it a top jet, the network will just say, it's not a QCD jet. It's something else. I mean, of course, it has never seen top jets. It doesn't know if it's a top jet. So like, but it's a QCD jet. It's one of my favorite problems, and it's one of those problems where I'm not sure we're going to solve it eventually to make it. And there's two questions, right? The first is standard ways of doing anomaly searches. Just as you know, just measure compressibility. Like autoencoders measure compressibility. Or in other words, it is very different to, like if a top jet is more complex than a QCD jet, the autoencoder might find a top jet in the QCD sample, but if dark matter jets are simpler than QCD jets, it would never find those in the QCD sample because they're simpler and simpler. It doesn't tag, right? So the first question is, like, am I not introducing a huge bias? And if I want a bias, how do I control it? And the second question is, how do I do statistics? I mean, you know all of this, I'll just explain this to everybody else. How do I do statistics with that, right? I mean, what is my anomaly score worth as a statistics measure? Which I think is an unsolved problem. Just to say, like, I am, of course, prepared, and this is the plot that I gave you guys to show. So this is a latent representation of QCD on top jets, so trained on QCD jets. The blue QCD, the green QCD jets are here, and the top jets are blue, and they're somewhere else. So the network can tell them apart. The question is, what do I do with it? CMS is running a trigger, right? It's actually using a normalized autoencoder trigger. I think they will find events where the detectors didn't work so well, is my guess. But it's one of these, like, big questions, yeah. And it comes, of course, along the same lines. The more analysis we want to do at the LHC, right, we will be person power limited, which means at some point, if you have petabytes a second, a lot of that data nobody will ever look at. So shouldn't we at least run an anomaly search over it to make sure that nothing really dramatically weird happens there? And there the answer is, I think, yes. So I would think, like, use it, and then when it turns up something, who knows what we'll do with it. But I would never say no. Use it, play with it, do something. Like, whatever. You see, if you're the person, or if you are the person writing the autoencoder that finds an anomaly in CMS, and that anomaly is a new particle, you're going to get a Nobel Prize for it. I think I would take that risk. Sorry for looking at some person.
Okay, any more questions, comments?
Just for one last thing for the students, so my slides are going to be there somewhere now. I linked our lecture notes. This is my group, like, we're writing lecture notes. The lecture notes are not that important. I mean, you get lectures on the same topic. In that lecture notes, you find a link to a Git, the group GitHub, and a Git repository. And there is tutorial versions of a lot of codes that we use for machine learning research. So if you're interested in playing with stuff, just play. If something doesn't work, send me an email, send us feedback, because my students and postdocs, they have great fun in maintaining this little library of tutorials, and then, like, maybe you can have some fun with it. Maybe it's a fast step into research.
So I haven't, yeah, so beside exploring the landscape of string theory and vacua, let's say, and,
yes.
So are there contributions that machine learning can do for theory beside what you described, so like more on the side of the hard theory, let's say, side of the story?
It depends how hard do you want it. So multi-loop calculations in QCD, is that hard enough? I think you can do a lot of things, right? But calculating the loops, doing integrations, like, encoding them. So I think, so in hard, like, quantum field theory kind of thing, a million things. Similar to Pheno, where we basically turn everything around. There are these ideas about looking, like, at the landscape, the BSM landscape of stuff, like, new models, scan them. That's maybe more Pheno eventually, because you always want to contrast with data. There are beautiful papers on how to discover symmetries in the LHC dataset, which is great. My hopes on that one are relatively low. I fear we know the symmetries in the LHC dataset, from the symmetries of the detector to the gauge symmetries of our non-abelian quantum field theory gauge theory, but maybe not. And then maybe for other fields where you want to run these kind of more theoretical things on other data sets, you might find I'm thinking about like Cosmo Astro data sets, right? You might find structures and symmetries there that really nobody has thought about, because these data sets are way more complex. Right? I showed you our data is not very complicated, really. Like, it's a bunch of energy momenta. But I talked about the SKA, square-kilometer array, right? I mean, it's very different. It's hugely complex data. It's an absolute nightmare. It's it's antennas, interference patterns of square-kilometer of antennas, right? I mean, you'll find structure there, and that is more theoretical, because then you might be able to map this to cosmological properties. Do the same for LHC. It's just my hopes are low, but that shouldn't stop you.
I think you might symbolic regression, for instance, for group calculations and all these things that someone is trying to develop. It's not
I have worked on symbolic regression, and it's a little bit of a disappointment. It's like, it turns out turning data sets into formulas is harder than I thought. If you could, yes. Symbolic regression, basically the idea is I have a data set, I want to describe it by a formula. Another thing is identify differential equations that describe your formula of your data sets. That's probably easier than a closed formula. So these kind of structure searching things, they usually go under the name of physics-inspired neural networks. Yes, absolutely. Yeah. My point would be, anything, do it, right? Make the breakthrough, try it. You'll never know that it doesn't work until you've tried. My microphone.
No, works. It takes a while. If there are no more questions, let's thank Tilman again. So especially for the students who are too shy to raise your hand, you can chat to Tilman.
I'm here.
He's here today, and there's refreshments outside. And I guess that's it for this year colloquium. We'll resume probably in March. Thank you.